In this presentation, I will be sharing the capabilities of the new graphics engine based on the Apple Metal API. Before I start showing features of the new graphics engine, I would like to discuss three important rendering techniques. First technique is a deferred lighting technique. Deferred lighting can render considerable number of lights more easily than forward lighting. With forward lighting, in a scene with an enormous number of lights, it is impossible for every fragment to calculate the contribution of every light without a significant performance hit. For a deferred lighting, only one geometry pass required, and each light computed only for those pixels that it affects in the scene. A deferred lighting consists of two passes. On the first pass, the renderer transforms and draws the scene's models, and the fragment function output the results to a set of textures known as the G-buffer. The G-buffer contains material colors from the models, as well as per fragment albedo, normal, depth, and other values. On the second pass, the renderer draws each light volume, using the G-buffer data to apply the lighting calculations for each pixel. Finally, the renderer composites per pixel data such as shadow and directional lighting onto the scene by executing a full-screen quad render. One key disadvantage of a deferred lighting technique is high GPU memory consumption and system memory bandwidth. The Apple Silicon GPU is built on a tile-based deferred rendering architecture, which allows to render data to tile memory within the GPU. By rendering G-buffer data to a tile memory, the device avoids expensive round trips between the GPU and the system memory. This allows fragment shaders to read from and perform calculations on rendered targets in a tile memory before this data is written to the tile memory again. This feature allows to avoid storing a G-buffer data in a system memory between the first and the second render passes. Thus, a deferred lighting renderer implemented within a single render pass. System memory does not need to be allocated for a G-buffer, and each of these textures declared within a memoryless storage mode. The next rendering technique is ray tracing. It works by tracing a path from the camera through each pixel in a virtual screen and calculating the color of the object visible through it. Ray tracing-based rendering provide a realistic simulation of light transport as compared to traditional rasterization techniques. Reflections have traditionally been difficult for rasterization. Reflection probes is a technique that works well but limited in resolution, requires filtering, and struggles with dynamic geometry. With ray-traced reflections, we can rely on the scene information in the Metal API acceleration structure. First, we take the incident ray from the camera's position to the point. Then, we reflect this point on the normal associated with the point. This provides us with a direction we can trace a ray towards to and find any reflected scene objects. Ray tracing types are supported in vertex, fragment, and tile functions since Metal API 2.4. It is possible to input compacted acceleration structure to the fragment shader. This makes it possible to use the G-buffer render pass to shade visible pixels, considering reflection data. Ray-traced reflection within single render pass is a significant performance optimization in terms of saving memory bandwidth. We calculate reflections in a fragment function with the vertex normal and vertex world space positions from a G-buffer and information coming from the acceleration structure. Primitive acceleration structures are composed of individual pieces of geometry ray-traced intersections and require accessing vertex data and resources from the fragment function directly. For these cases, we need to make sure that the GPU has an access to the data that it needs to apply our shading equations to. This is achieved with a bindless binding model, which is represented as argument buffers in the Metal API. In this case, we can manage ray-traced intersections with geometry that lies completely outside of the viewing frustum to produce accurate reflections. Well, we have the ray tracing technique for correct reflections using the metal acceleration structures. But what if we need to render the scene with a considerable number of dynamic objects? A scene with dynamic objects will require rebuilding acceleration structures that are very computationally expensive. Now, metal acceleration structures support two-level instancing of primitive acceleration structures. We can update only matrices that determine the position and orientation of dynamic objects in the world space. This step does not require rebuilding the entire acceleration structure within mesh geometry. Metal API supports acceleration structures refitting, which is combined with instancing to support dynamic objects in the scene. Finally, metal acceleration structures also support compaction, which is used to reclaim significant amounts of memory once an acceleration structure is built. In this demo, we see correctly rendered ray-traced reflections from both static and dynamic objects. We highlight pixels with the red color where reflections are correctly calculated from shaded surfaces. This effect is difficult to achieve within a traditional rasterization technique. Before showing another ray traced demo, let us focus on the modern fire rendering technique. Most modern video games use 2D sprites for fire rendering. This technique struggles with scene geometry intersections. Also, this rendering technique does not allow physical simulation of a fire that responds to the wind or turbulent vortices. No doubt that a physically based fire animation provides the most stunning visual effects in computer graphics, but it has historically been the domain of a high-quality offline rendering due to the great computational cost. Let us focus on a physically based fire animation. In physics, it is common to make simplifying assumptions when modeling. We can simulate fire as an incompressible, homogeneous fluid model. We simulate fluid dynamics on a regular Cartesian grid with 3D space spatial coordinates and time variable. The fluid is represented by its velocity field and a scalar pressure field. These fields vary in both space and time. State of the fluid over time is described by the Navier-Stokes equations for incompressible flow. Compute shaders are used to calculate velocity and pressure fields over time. The result of a fluid simulation is a collection of values stored in a 3D texture. However, there is no mechanism in the metal for rendering these 3D textures directly. Therefore, we render the fire volume using a ray marching fragment function. We render the full screen quad using a fragment function so we know exactly where the ray from the camera enters the volume, in which direction it is traveling, and the number of samples to take from the 3D texture. We render the fire by marching rays through the volume and accumulating densities from the 3D texture. To produce ray-traced reflections, we put fire volume as a bound box mesh into the metal acceleration structure. First, we take the incident ray from the camera's position to the point. Then, we reflect this point on the normal associated with it. This provides us with a direction for a fire volume ray marching. Then we render the reflections by marching rays through the volume and accumulating densities from the 3D texture. This demo provides accurate reflections for the physically based fire volumes.